Part 2, Chapter 12, Part 2 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Mary Agnes Clerke. Chapter 12, Stars and Nebulae, Part 2. A fairly complete preliminary answer to the question, "What are the stars made of?" was given by Sir William Huggins in 1864. By laborious processes of comparison between stellar dark lines and the bright rays emitted by terrestrial substances, he sought to assure his conclusions regardless of cost in time and pains. He averred, indeed, that, taking into account restrictions by weather and position, the thorough investigation of a single star spectrum would be the work of some years. Of two, however, those of Betelgeuse and Aldebaran, he was able to furnish detailed and accurate drawings. The dusky flutings in the prismatic light of the first of these stars have not been identified with the absorption of any particular substance, but associated with them are metallic lines, of which 78 were measured and a good many identified by Huggins, while the wavelengths of 97 were determined by Vogel in 1871. A photographic research made by Keeler at the Allegheny Observatory in 1897 convinced him that the linear spectrum of third-type stars of the Betelgeuse pattern essentially repeats that of the Sun, but with marked differences in the comparative strength of its components. Hydrogen rays are inconspicuously present. That an exalted temperature reigns, at least in the lower strata of the atmosphere, is certified by the vaporization there of matter so refractory to heat as iron. 9 elements, among them iron, sodium, calcium, and magnesium, were recognized by Huggins as having stamped their signature on the spectrum of Aldebaran, while the existence in Sirius and nearly all the other stars inspected of hydrogen, together with sundry metals, was rendered certain or highly probable. This was admitted to be a bare gleaning of results, nor is there reason to suppose any of his congeners inferior to our Sun in complexity of constitution. Definite knowledge on the subject, however, made little advance beyond the point to which it was brought by Huggins's early experiments, until spectroscopic photography became thoroughly effective as a means of research. In this, as in so many other directions, Sir William Huggins acted as pioneer. In March 1863 he obtained microscopic prints of the spectra of Sirius and Capella, but they told nothing. No lines were visible in them. They were mere characterless streaks of light. 9 years later, Dr. Henry Draper of New York got an impression of 4 lines in the spectrum of Vega. Then Huggins attacked the subject again in 1876, when the 18-inch speculum of the Royal Society had come into his possession, using prisms of Iceland spar and lenses of rock crystal, and this time with better success. A photograph of the spectrum of Vega showed 7 strong lines. Still, he was not satisfied. He waited and worked for 3 years longer. At length, on December 18, 1879, he was able to communicate to the Royal Society results answering to his expectations. The delicacy of eye and hand needed to obtain them may be estimated from the single fact that the image of a star had to be kept, by continual minute adjustments, exactly projected upon a slit 1/350 of an inch in width during nearly an hour, in order to give it time to imprint the characters of its analyzed light upon a gelatine plate raised to the highest pitch of sensitiveness. But by this time he had secured in his wife a rarely qualified assistant. The ultraviolet spectrum of the white stars, of which Vega was taken as the type, was thus shown to be a very remarkable one. A group of broad dark lines intersected it, arranged at intervals, diminishing regularly upward, and falling into a rhythmical succession with the visible hydrogen lines. All belonged presumably to the same substance, and the presumption was rendered a certainty by direct photographs of the hydrogen spectrum taken by H.W. Vogel at Berlin a few months earlier. In them 7 of the white star series of grouped lines were visible, and the full complement of 12 appeared on Cornu's plates in 1886. In yellow stars, such as Capella and Arcturus, the same rhythmical series was partially represented, but associated with a great number of other lines, their state as regards ultraviolet absorption approximating to that of the sun, while the redder stars betrayed so marked a deficiency in actinic rays that from Betelgeuse, with an exposure 40 times that required for Sirius, only a faint spectral impression could be obtained, and from Aldebaran, in the strictly invisible region, almost none at all. Thus, by the means of stellar light analysis, acquaintance was first made with the ultraviolet spectrum of hydrogen, and its harmonic character, as expressed by Balmer's law, supplies a sure test for discriminating among newly discovered lines those that appertain from those that are unrelated to it. Delandre's 5 additional prominence rays, for instance, were at once seen to make part of the series, because conforming to its law, while a group of 6 dusky bands, photographed by Sir William and Lady Huggins, April 4, 1890, near the extreme upper end of the spectrum of Sirius, were pronounced without hesitation, for the opposite reason, to have nothing to do with hydrogen. Their true affinities are still a matter for inquiry. As regards the hydrogen spectrum, however, the stars had further information in reserve. Until recently it was supposed to consist of a single harmonic series, although by analogy 3 should coexist. In 1896, accordingly, a second, bound to the first by unmistakable numerical relationships, was recognized by Professor Pickering in spectrographs of the 2.5 magnitude star Zeta Puppis, and the identification was shortly afterwards extended to prominent Wolf-Rayet emission lines. The discovery was capped by Dr. Rydberg's indication of the Wolf-Rayet blue band at lambda 4688 as the fundamental member of the third and principal hydrogen series. None of the Pickering lines, as they may be called to distinguish them from the Huggins series, can be induced to glimmer in vacuum tubes. They seem to characterize bodies in a primitive state, and are in many cases associated with absorption rays of oxygen, the identification of which by Mr. Maclean in 1897 was fully confirmed by Sir David Gill. The typical oxygen star is Beta Crucis, one of the brilliants of the Southern Cross, but the distinctive notes of its spectrum occur in not a few specimens of the helium class. Thus Sir William and Lady Huggins photographed several ultraviolet oxygen lines in Beta Lyrae, and found in Rigel signs of the presence of nitrogen, which, as well as silicium, proves to be a tolerably frequent constituent of such orbs. For some unknown reason, metalloids tend to become effaced, as metals, in the normal course of stellar development, exert a more and more conspicuous action. Dr. Schneider's spectrographic researches at Potsdam in 1890 and subsequently exemplify the immense advantages of self-registration. In a restricted section of the spectrum of Capella, he was enabled to determine nearly 300 lines with more precision than had then been attained in the measurement of terrestrial spectra. This star appeared to be virtually identical with the Sun in physical constitution, although it emits, according to the best available data, about 140 times as much light, and is hence presumably 1,600 times more voluminous. An equally close examination of the spectrum of Betelgeuse showed the predominance in it of the linear absorption of iron, but its characteristic flutings do not extend to the photographic region. Spectra of the second and third orders are for this reason not easily distinguished on the sensitive plate. A spectrographic investigation of all the brighter northern stars was set on foot in 1886 at the Observatory of Harvard College under the form of a memorial to Dr. H. Draper, whose promising work in that line was brought to a close by his premature death in 1882. No individual exertions could, however, have realized a tithe of what has been and is being accomplished under Professor Pickering's able direction, with the aid of the Draper and other instruments, supplemented by Mrs. Draper's liberal provision of funds. A novel system was adopted, or rather an old one, originally used by Fraunhofer, was revived. The use of a slit was discarded as unnecessary for objects like the stars, devoid of sensible dimensions and giving hence a naturally pure spectrum; and a large prism placed in front of the object glass analysed at once, with slight loss of light, the rays of all the stars in the field. Their spectra were taken, as it were, wholesale. As many as 200 stars, down to the 8th magnitude, were occasionally printed on a single plate with a single exposure. No cylindrical lens was employed. The movement of the stars themselves was turned to account for giving the desirable width to their spectra. The star was allowed, by disconnecting or suitably regulating the clock, to travel slowly across the line of its own dispersed light, so broadening it gradually into a band. Excellent results were secured in this way. About 50 lines appear in the photographed spectrum of Aldebaran, and 8 in that of Vega. On January 26, 1886, an exposure of 34 minutes, a simultaneous impression was obtained of the spectra, among many others, of close upon 40 Pleiades. With few and doubtful exceptions, they all proved to belong to the same type. An additional argument for the common origin of the stars forming this beautiful group was thus provided. The Draper Catalogue of Stellar Spectra was published in 1890. It gives the results of a rapid analytical survey of the heavens north of 25 degrees of southern declination, and includes 10,351 stars down to about the 8th magnitude. The telescope used was of 8 inches aperture and 45 focus, its field of view, owing to the portrait lens or doublet form given to it, embracing with fair definition no less than 100 square degrees. An objective prism 8 inches square was attached, and exposures of a few minutes were given to the most sensitive plates that could be procured. In this way the sky was twice covered in duplicate, each star appearing, as a rule, on 4 plates. The registration of their spectra was sought to be made more distinctive than had previously been attempted, Secchi's first type being divided into 4, his second into 5 subdivisions, but the differences regarded in them could be confidently established only for stars above the 6th magnitude. The work supplies none the less valuable materials for general inferences as to the distribution and relations of the spectral types. The labour of its actual preparation was borne by a staff of ladies under the direction of Mrs. Fleming. Materials for its completion to the southern pole have been accumulated with the identical instrument used at Cambridge, transferred for the purpose in 1899 to Peru, and the forthcoming second Draper Catalogue will comprise 30,000 stars in both hemispheres. As supplements to this great enterprise, 2 important detailed discussions of stellar spectra were issued in 1897 and 1901 respectively. The first, by Miss A. C. Maury, dealt with 681 bright stars visible in the northern hemisphere; the second, by Miss A. J. Cannon, with 1,122 southern stars. Both authors traced with care and ability the minute gradations by which the long process of stellar evolution appears to be accomplished. The progress of the Draper Memorial researches was marked by discoveries of an unexampled kind. The principle upon which motion in the line of sight can be detected and measured with the spectroscope has already been explained. It depends, as our readers will remember, upon the removal of certain lines, dark or bright, it matters not which, from their normal places by almost infinitesimal amounts. The whole spectrum of the moving object, in fact, is very slightly shoved hither or thither according as it is travelling towards or from the eye. But for convenience of measurement, one line is usually picked out from the rest, and attention concentrated upon it. The application of this method to the stars, however, is encompassed with difficulties. It needs a powerfully dispersive spectroscope to show line displacements of the minute order in question, and powerful dispersion involves a strictly proportionate enfeeblement of light. This, where the supply is already to a deplorable extent niggardly, can ill be afforded, for which reason the operation of determining a star's approach or recession is, even apart from atmospheric obstacles, an excessively delicate one. It was first executed by Sir William Huggins early in 1868, selecting the brightest star in the heavens as the most promising subject of experiment. He considered the F line in the spectrum of Sirius to be just so much displaced towards the red as to indicate, the orbital motion of the earth being deducted, recession at the rate of 29 miles a second, and the reality and direction of the movement were ratified by Vogel and Loss's observation, March 22, 1871, of a similar but even more considerable displacement. The inquiry was resumed by Huggins with improved apparatus in the following year, when the velocities of 30 stars were approximately determined. The retreat of Sirius, which proved slower than had at first been supposed, was now announced to be shared, at rates varying from 12 to 29 miles, by Betelgeuse, Rigel, Castor, Regulus, and 5 of the principal stars in the Plough. Arcturus, on the contrary, gave signs of rapid approach, as well as Pollux, Vega, Deneb in the Swan, and the brightness of the Pointers. Numerically, indeed, these results were encompassed with uncertainty. Thus Arcturus is now fully ascertained to be travelling towards the sun at the comparatively slow pace of less than 5 miles a second, and Sirius moves twice as fast in the same direction. The great difficulty of measuring so distended a line as the Sirian F might indeed well account for some apparent anomalies. The scope of Sir William Huggins's achievement was not, however, to provide definitive data, but to establish as practicable the method of procuring them. In this he was thoroughly successful, and his success was of incalculable value. Spectroscopic investigations of stellar movements may confidently be expected to play a leading part in the unravelment of the vast and complex relations which we can dimly detect as prevailing among the innumerable orbs of the sidereal world, for it supplements the means which we possess of measuring by direct observation movements transverse to the line of sight, and thus completes our knowledge of the courses and velocities of stars at ascertained distances, while supplying for all a valuable index to the amount of perspective foreshortening of apparent movement. Thus some, even if an imperfect, knowledge may at length be gained of the revolutions of the stars, of the systems they unite to form, of the paths they respectively pursue, and of the forces under the compulsion of which they travel. The applicability of the method to determining the orbital motions of double stars was pointed out by Fox Talbot in 1871, but its use for their discovery revealed itself spontaneously through the Harvard College photographs. In spectrograms of Ursae Majoris Mizar, taken in 1887 and again in 1889, the K line was seen to be double, while on other plates it appeared single. A careful study of Miss A. C. Maury of a series of 70 impressions indicated for the doubling a period of 52 days, and showed it to affect all the lines in the spectrum. The only available, and no doubt the true, explanation of the phenomenon was that two similar and nearly equal stars are here merged into one telescopically indivisible, their combined light giving a single or double spectrum, according as their orbital velocities are directed across or along our line of sight. The movements of a revolving pair of stars must always be opposite in sense and proportionately equal in amount. That is, they all at times travel with speeds in the inverse ratio of their masses. Hence, unless the plane of their orbits be perpendicular to a plane passing through the eye, there must be two opposite points where their velocities in the line of sight reach a maximum, and two diametrically opposite points where they touch zero. The lines in their common spectrum would thus appear alternately double and single twice in the course of each revolution. To that of Mazar, at first supposed to need 104 days for its completion, a period of only 20 days, 14 hours, was finally assigned by Vogel. Anomalous spectral effects, probably due to the very considerable eccentricity of the orbit, long impeded its satisfactory determination. The mean distance apart of the component stars, as now ascertained, is just 22 million miles, and their joint mass quadruples that of the sun. But these are minimum estimates, for if the orbital plane be inclined, much or little, to the line of sight, the dimensions and mass of the system should be proportionately increased. An analogous discovery was made by Miss Maury in 1889, but in the spectrum of Beta Aurigæ the lines open out and close up on alternate days, indicating a relative orbit with a radius of less than 8 million miles, traversed in about 4 days. This implies a rate of travel for each star of 65 miles a second, and a combined mass 4.7 times that of the sun. The components are approximately equal both in mass and light, and the system formed by them is transported towards us with a speed of some 16 miles a second. The lines, shifting so singularly communicative, proceed in this star with perfect regularity. This new class of spectroscopic binaries could never have been visually disclosed. The distance of Beta Aurigæ from the earth, as determined somewhat doubtfully by Professor Pritchard, is nearly 3 1/3 million times that of the earth from the sun. Parallax equals 0.06 minutes. Whence it has been calculated that the greatest angular separation of the revolving stars is only 5,000ths of a second of arc. To make this evanescent interval perceptible, a telescope 80 feet in aperture would be required. The zodiacal star Spica Alpha Virginis was announced by Dr. Vogel April 24, 1890, to belong to the novel category, with the difference, however, of possessing a nearly dark instead of a brilliantly lustrous companion. In this case, accordingly, the telltale spectroscopic variations consist merely in a slight swinging to and fro of single lines. No second spectrum leaves a legible trace on the plate. Spica revolves in 4 days at the rate of 57 miles a second, or quicker, in proportion as its orbit is more inclined to the line of sight, round a centre at a minimum distance of 3 millions of miles. But the position of the second star being unknown, the mass of the system remains indeterminate. The lesser component of the splendid, slowly revolving binary, Castor, is also closely double. Its spectral lines were found by Bélopolsky in 1896 to oscillate once in nearly 3 days, the secondary globe being apparently quite obscure. Further study of the movements thus betrayed elicited the fact that the major axis of the eclipse traversed revolves in a period of 2,100 days, as a consequence most likely of the flattened shape of the stars. Still more unexpected was the simultaneous assignment by Campbell and Newell of a duplex character to Capella. Here both components shine, though with a different quality of light, one giving a pure solar spectrum, the other claiming prismatic affinity with Procyon. Their mutual circulation is performed in 104 days, and the radius of their orbit cannot be less, and may be a great deal more, than 51 million miles. Hence the possibility is not excluded that the star, which has an authentic parallax of 0.08 minutes, may be visually resolved. Indeed, signs of elongation were thought to be perceptible with the Greenwich 28-inch refractor, while only round images could be seen at Lick. Another noteworthy case is that of Polaris, found by Campbell to have certainly one, and probably two, obscure attendants. Through his systematic investigations of stellar radial velocities with the Mills spectrograph, knowledge in this department has, since 1897, progressed so rapidly that the spectroscopic binaries of our acquaintance already number 100, and 10 times as many more doubtless lie within easy range of detection. Now it is evident that a spectroscopic binary, if the plane of its motion made a very small angle with the line of sight, would be a variable star. For during a few hours of each revolution, some at least of its light should be cut off by a transit of its dusky companion. Such eclipse stars are actually found in the heavens. The best and longest known member of the group is Algol, in the head of Medusa, the demon star of the Arabs. This remarkable object, normally above the third magnitude, loses and regains 3/5 of its light once in 68.8 hours, the change being completed in about 12 hours. Its definite and limited nature and punctual recurrence suggested to Goodricke of York, by whom the periodicity of the star was discovered in 1783, the interposition of a large dark satellite. But the conditions involved by the explanation were first seriously investigated by Pickering in 1880. He found that the phenomena could be satisfactorily accounted for by supposing an obscure body 0.764, the bright star's diameter, to revolve round it in a period identical with that of its observed variation. This theoretical forecast was verified with singular exactitude at Potsdam in 1889. A series of spectral photographs taken there showed each of Algol's minima to be preceded by a rapid recession from the earth, and succeeded by a rapid movement of approach towards it. They take place accordingly when the star is at the furthest point from ourselves of an orbit described round an invisible companion, the transits of which across its disk betray themselves to notice by the luminous vicissitudes they occasion. The diameter of this orbit, traversed at the rate of 26 miles a second, is just 2,000,000 miles. And it is an easy further inference from the duration and extent of the phases exhibited that Algol itself must be, in round numbers, 1,000,000, its attendant 830,000 miles in diameter. Assuming both to be of the same density, Vogel found their respective masses to be 4/9 and 2/9 that of the sun, and their distance asunder to be 3,230,000 miles. This singularly assorted pair of stars possibly form part of a larger system. Their period of revolution is shorter now by 6 seconds than it was in Goodricke's time, and Dr. Chandler has shown by an exhaustive discussion that its inequalities are comprised in a cycle of about 130 years. They arise, in his view, from a common revolution in that period of the close couple, about a third distant body emitting little or no light, in an orbit inclined 20 degrees to our line of vision, and of approximately the size of that described by Uranus round the sun. The time spent by light in crossing this orbit causes an apparent delay in the phases of the variable, when Algol and its eclipsing satellite are on its further side from ourselves, balanced by acceleration, while they traverse its hither side. Dr. Chandler derives confirmation for his plausible and ingenious theory from a supposed undulation in the line traced out by Algol's small proper motion, but the reality of this disturbance has yet to be established. Meanwhile, M. Tisserand, late director of the Paris Observatory, preferred to account for Algol's inequalities on the principle later applied by Bélopolsky to those of Castor. That is to say, he assumed a revolving line of apsides in an elliptical orbit traversed by a pretty strongly compressed pair of globes. The truth of this hypothesis can be tested by close observation of the phases of the star during the next few years. The variable in the head of Medusa is the exemplar of a class including 26 recognized members, all of which doubtless represent occulting combinations of stars, but their occultations result merely from the accident of their orbital planes passing through our line of sight. Hence the heavens must contain numerous systems similarly constituted, though otherwise situated as regards ourselves, some of which, like Spica Virginis, will become known through their spectroscopic changes, while others, because revolving in planes nearly tangent to the sphere or at right angles to the visual line, may never disclose to us their true nature. Among eclipsing stars should probably be reckoned the peculiar variables Beta Lyrae and V Puppis, each believed to consist of a pair of bright stars revolving almost in contact. Three stars, on the other hand, distinguished by rapid and regular fluctuations, have been proved by Bélopolsky to be attended by non-occulting satellites, which circulate nevertheless in the identical periods of light change. Gore's Catalogue of Known Variables included in 1884 190 entries, and the number was augmented to 243 on its revision in 1888. Chandler's first list of 225 such objects, published about the same time, received successive expansions in 1893 and 1896, and finally included 400 entries. A new catalogue of variable stars, still wider in scope, will shortly be issued by the German Astronomische Gesellschaft. Mr. A. W. Roberts's researches on southern variables have greatly helped to give precision, while adding to the extent of knowledge in this branch. Dr. Gould held the opinion that most stars fluctuate slightly in brightness through surface alterations similar to, but on a larger scale than, those of the sun, and the solar analogy might be pushed somewhat further. It perhaps affords a clue to much that is perplexing in stellar behaviour. Wolf pointed out in 1852 the striking resemblance in character between curves representing sun-spot frequency and curves representing the changing luminous intensity of many variable stars. There were the same steep ascent to maximum and more gradual decline to minimum, the same irregularities in heights and hollows, and, it may be added, the same tendency to a double maximum and complexity of superposed periods. It is impossible to compare the two sets of phenomena thus graphically portrayed without reaching the conclusion that they are of closely related origin. But the correspondence indicated is not, as has often been hastily assumed, between maxima of some spots and minima of stellar brightness, but just the reverse. The luminous outbursts, not the obscurations of variable stars, obey a law analogous to that governing the development of spots on the sun. Objects of the kind do not then gain light through the closing up of dusky chasms in their photospheres, but by an actual increase of surface brilliancy, together with an immense growth of these brilliant formations, prominences and faculae, which in the sun accompany or are appended to spots. A comparison of light curves with curves of spot frequency leaves no doubt on this point, and the strongest corroborative evidence is derived from the emergence of bright lines in the spectra of long-period variables rising to their recurring maxima. End of Chapter 12, Part 2.